Hi, I'm Bob Rau. I'm with Hewlett-Packard Labs, and I'll be talking to you today about instruction-level parallelism, or ILP for short. More specifically, I'll talk to you about compiling for ILP. Instruction-level parallelism is a style of processing which has its roots back in the 1960s when the historic CDC 6600 and the IBM 36091 were brought out. Thereafter, it went into a period of dormancy in the 70s. In the 80s, it began to re-emerge in the form of mini supercomputer companies and products. And today, there's scarcely a microprocessor that aspires to high performance levels that does not have some form of ILP in it. Now, ILP is a form of processing, unlike normal parallel processing, where in normal parallel processing, the task is chopped up into fairly large chunks of computation, typically by a programmer, and handed out to individual processors to execute. In contrast, ILP attempts to get parallelism within a single processor by working with units of computation at the level of ordinary RISC instructions. So these might be integer operations, floating point multipliers, etc., and tries to achieve the parallelism by executing multiple of these in parallel. Now, any form of an instruction-level parallel processor requires the ability, obviously, to execute multiple operations in parallel. Now, the simplest type of a functional unit, and by a functional unit I mean something like an integer ALU or a floating point functional unit, can only execute one operation at a time, and so clearly there's no opportunity for parallelism there. There are two ways of going about getting the additional parallelism. One is to replicate the functional units, to have multiple functional units, each of which can do only one operation at a time. However, by virtue of having many of these, we can have many of these operations going on at the same time. The cost involved is that you have to replicate the entire hardware, plus there are many secondary but very important problems having to do with the busing to such a structure. An alternative approach is what is known as pipelining, where the computational logic in one of these units is chopped up into chunks separated by pipeline stages. And this operates much like an assembly line. Once one starts off one operation and it moves on to the next stage, a second operation can begin even while the first one is still in execution. In this form of a unit, we can once again have 4 operations executing at any point in time, and it is largely equivalent in terms of its level of parallelism to this structure. At some point, however, adding additional stages here begins to be not the ideal solution, since there is as much time spent in waiting between stages as there is in computing within each stage. And at that point, we might want to once again go ahead and replicate these pipeline functional units, giving us an execution unit which has multiple pipeline functional units. Now, in sequential machines, originally this was the style of functional unit. In RISC processors, it evolved slowly to this. And we are interested in something which is very much more like this, with much more opportunity for instruction-level parallelism. Now, let's look at how the instruction-level execution is actually achieved. The final goal, as I mentioned, is to have multiple operations, each of which is like a RISC-level operation, being issued in parallel, executing in parallel. Now, let's contrast it to the original situation. We start off with a program. And if we were to execute this program and record it almost as if we had a logic analyzer attached to it, we might find that this is the sequence of instructions executed, and it takes a certain amount of time. What an optimizing compiler attempts to do is to take this original program, come up with an optimized program, in which as much as possible of the redundant computation has been removed. The record of execution for such a program would be somewhat shorter because the redundant computations have been removed. Now, an ILP compiler, an ILP system, assumes that you have all of this optimization capability. But beyond that, it attempts to take this record of execution, which is relatively long, and to compress it to a shorter record of execution by executing multiple of these in parallel. So what we'll be looking at is primarily this part of it. How does one, between the compiler and the hardware, achieve this style of execution, this record of execution, rather than this one over here? Now, one way or the other, regardless of whether this is done by hardware or by software, there are three major activities that have to be performed. We start off with the original program, sequential code, where the default is that every operation is dependent on every other operation, unless we prove otherwise. So the first step is to expose the parallelism that is implicit in this program, and to express the program in a different form, where every operation is assumed to be independent of every other operation, unless there's an explicit dependence edge that goes from one to the other, indicating that this one can only execute after that one. So this major activity here is one of analyzing the dependencies between these operations to prove to oneself that, in fact, an operation is independent of another one. And in this form, the parallelism is quite a bit more explicit. It's clear that these two could be executed in parallel, and then these two, and so forth. Now, if this amount of parallelism is adequate to make use of the hardware that we have to keep it fully utilized, that's fine. If not, we have to have a further step of enhancing the parallelism, which essentially corresponds to transforming the program, rewriting the program in some way, so that the height of this computation is reduced at the expense of making it wider. Well, in fact, that is the objective. Now that we've got the requisite amount of parallelism, we go ahead to exploit it and to achieve an execution in which we have multiple operations being issued in parallel and a relatively short record of execution. So there are three broad styles of processor that people talk about, which have instruction level capability. One is the very long instruction word processor, or VLIW for short. And in this style of computing, the bulk of the effort on doing this ILP, on orchestrating the ILP, is on the compiler, which is why we call it, you could characterize this as a smart compiler. The hardware itself is as simple as it gets. It essentially takes the plan of execution that has been prepared by the compiler, and then it goes ahead and does precisely what has been called for. So you might characterize this as dumb hardware and a smart compiler. The other style of ILP processor is the superscalar processor, where the idea is that all the smarts reside in the hardware, that it will, at runtime, find this parallelism, make use of it. And the compiler, therefore, need not be any smarter than a regular optimizing compiler. In the next few slides, we'll look at how these two approaches contrast with one another. Now, in both of these cases, the hardware is capable of issuing multiple operations per cycle. There's another alternative, which is to speed up the cycle time, pipeline your functional units much more deeply, and then issue only one operation per cycle. I want to point out that from the compiler's point of view, there's little difference between these three. Eventually, what the compiler is concerned with is how much ILP does it need to be able to find and exploit. And that is determined by the number of functional units multiplied by the pipeline depth of the functional units. And it really doesn't matter whether you've got a number of units which are pipelined to a lesser extent or fewer units that are pipelined to a greater extent. The compiler's task is much the same. Now, when compiling for ILP, as I said, the major burden of finding the ILP and exploiting it is on the compiler. So the compiler goes through these steps that are already described. And finally, it comes up with VLIW code, which is a very explicit plan of execution, which says precisely which operation should be executed on which functional unit and at what point in time. And then the hardware's role is to just literally do what it's been told and to take all the instructions that have been packed into one VLIW instruction, issue them in parallel, and then move on. So once again, the entire burden is on the compiler to go through these various steps. In the case of the superscalar machine, at least in its original conception, the view was that the hardware would do all that was needed. So the idea was that the processor would have what's called a window, an instruction window, on the program that is executing. And within that instruction window, it would perform this analysis that was needed to figure out which operations were independent of which other operations. And then it would go ahead and immediately exploit the parallelism that it had found by making the decisions as to which operation should execute when and where. Now, there are two shortcomings with this approach. One is that the amount of parallelism that we find within this window might not be adequate to keep the machine busy. On the other hand, to try and make the window much broader so that we do find the amount of parallelism that we want ends up becoming inordinately expensive. The other problem is that any hope at all of enhancing parallelism, which is what we did over in the VLIW compiler, is pretty much impossible because that requires fairly significant surgery to the program. For these two reasons, the understanding has been arrived at that even superscalar machines do in fact need all of the compiling capability of a VLIW machine. And in this case, the compiler for a superscalar machine would once again go through all of these steps, exposing the parallelism, enhancing if need be, and then it would come up with a schedule, much as for a VLIW machine, which indicates which operations are expected to be issued at the same time. However, there's a final step which is different, which is that once we found all this parallelism and orchestrated it, we have to write it back in the form of a sequential program. And the reason is that this is the only form of code that the superscalar processor understands. So in a sense, we are throwing away information that we've gathered for the superscalar machine to re-extract at runtime. However, the point is that through having done this, we will hopefully have more parallelism in a small window than we had previously. Now, by and large, the compiler for a superscalar machine has been viewed as being essentially identical to the compiler for a VLIW machine. I'd like to point out towards the end of this talk how, in fact, there are some differences that need to be addressed. So just to summarize what we've gone through so far, an ILP compiler most definitely assumes the existence of a state-of-the-art machine-independent optimizer. In other words, ILP is not an alternative or a substitute for optimization. It builds upon it. But over and beyond that, we have these three additional activities: exposing ILP, which is primarily one of analysis; enhancing ILP, which is primarily an issue of transforming the program into a different, more parallel form; and then finally exploiting ILP, which is essentially a task of scheduling and register allocation. Just a couple of words about how an ILP compiler relates to some of the other compiler technologies that you might be familiar with. To begin with, of course, as I've said, all of the capability of an optimizing compiler is relevant in an ILP compiler. There are a couple of differences in terms of emphasis. In the optimizing compilers, the primary objective was to decrease the operation count. In an ILP compiler, the operation count is per se not that important. What's important is the schedule length that you derive. And in fact, during my sideroom days, I ran into a rather amusing example that highlighted this, where there was a benchmarking effort that was going on. And this individual had come up with a very complicated benchmarking program to figure out whether or not a particular compiler had a certain optimization capability. And he concluded that we had no optimization capability in the compiler. And the reason is that most of the operations that were being eliminated were off the critical path and were making no difference to the schedule length. So this is not to say that optimization is unimportant. It just shows you that that is not the primary objective in an ILP compiler. Vectorizing and parallelizing compilers differ quite substantially, in fact, almost totally, from an ILP compiler in terms of the way in which they exploit the parallelism that's found. In this case, it's worthwhile parallelism only if it's in the form of a vector instruction. In this case, only if it's in the form of multiple processes. However, the analysis that precedes both of these steps is extremely valuable in the ILP compiler as well. So what we will find is that an ILP compiler really draws on all these types of technologies, particularly in terms of analysis. But then there's this one big additional issue, which, as we'll find, really drives the whole compiler and its structure, namely scheduling, which is not that important over here. This talk has a companion talk that will go into some of the other issues, such as the enhancing and the exposing of ILP. In this particular talk, what I'm going to focus on is on exploiting ILP or scheduling. And we'll work our way upwards, starting with scheduling within the confines of a single basic block, then how we break out of that box so that we can increase the window of opportunity for parallelism across multiple basic blocks. Then how we go about actually doing scheduling across multiple basic blocks. Finally, a little bit about how scheduling for a superscalar machine differs from that for a VLIW. So let's start off with local scheduling. Now, scheduling is, in the final analysis, a matter of trying to decide which operation should be executed on which functional unit at which time. And so clearly, the quality of a scheduler is highly dependent on the quality of the model that it has, of the machine that it's working with. And here are four factors that determine how good a machine model one has. Firstly, since there's no machine around that has unbounded resources, it is clearly important that the scheduler understand that there are finite resources in a machine and that it be able to cope with that. Secondly, in most realistic machines, the functional units are not identical. You have floating point units that can do floating point operations, integer units that can do integer operations. And so a model in which you view every functional unit as being identical and interchangeable is unrealistic. The third factor has to do with the latencies that I assume. Now, by the latencies here, I'm talking about the actual hardware latencies, not the conceptual latency. For instance, in a superscalar machine, the conceptual latency is always 1. But the actual hardware latencies, for instance, for a floating point operation, might be 2 or 3 cycles. A scheduler that cannot understand that and schedule taking that into account clearly has less value. Finally, in any realistic machine, every operation has a fairly complex pattern of resource usage, which must be accurately modeled if we want to have a good schedule. Now, the importance of these differs somewhat between a VLIW compiler and a superscalar compiler. In a VLIW compiler, these are matters of correctness. If you have an incorrect machine model, you can end up with an incorrect schedule, which leads to an incorrect execution. In a superscalar machine, it's a little more forgiving, and all you get is poor performance, but the correctness is not necessarily compromised. To understand this issue of modeling the resource usage a little bit better, assume we have this kind of this simple little machine, which has an integer cluster over here and a floating point cluster over here. Now, if you think about, say, a floating point add, it's going to be executed over here in the floating point adder. But in addition, it uses certain other resources. For instance, on its first cycle of execution, it uses these 2 output ports of the floating point register file to get its source inputs. Then it might use the floating point adder for 1 cycle. And finally, it uses the result bus to write its result. Now, we have to be very careful that we do not schedule, say, a floating point add and a floating point multiply in such a way that they try and use either the source input buses or the result bus at the same time. The way this is done is by making use of something called a reservation table. And what I have here are the reservation tables for a floating point add and a floating point multiply. Now, let me just talk a little bit about the format of this table, zooming in on the titles over here. what we see is that we have a column in this table, one for every resource that is of interest. So we have the source bus 1, source bus 2, the result bus, the floating point adder, and the floating point multiplier. These are the different resources that the scheduler must keep track of. Over here, we have the time relative to the cycle on which the operation was issued. And so what this says is that on the first cycle of issue, the two source buses are used by the floating point add operation. On the next cycle, the floating point adder itself is used. And then on the third cycle, the result bus is used to send the result back to the register file. So this would correspond to a 3-cycle latency floating point add. Over here is the equivalent reservation table for a non-pipeline floating point multiply. Once again, we use the two source buses in the first cycle. We use the floating point multiplier for 3 cycles since it's non-pipeline, and then the result bus. If the floating point multiplier were pipelined, we would have a slightly different structure for it. So over here is the reservation table that we just saw for the non-pipeline floating point multiplier. If we have a pipeline floating point multiplier, then we have to break the multiplier down into 3 resources, the first stage, the second, and the third stage, and then we get this type of a structure. Now, the way this is used by the scheduler is to take this kind of pattern for each operation. So in this case, we have 2 floating point adds indicated by the orange and the green patterns, and then a floating point multiplier that is represented by the blue pattern. You can think of these almost like jigsaw puzzles, and the task of the scheduler is to fit these together in such a way that we minimize the execution time without ever using the same resource twice over. So over here, assuming there were no other constraints on how we could schedule it, this is what the scheduler might have come up with. Here's one floating point add, here's another floating point add, and here's the floating point multiply, all neatly interlocked, never using the same resource more than once. Now, in practice, the scheduler has to cope with more than just a resource usage pattern. It has to also take into account the fact that an operation cannot be scheduled before its inputs are ready, and in fact, a number of other such constraints. The scheduler does this by using a data structure called a data dependence graph, in which each vertex is represents one operation, and an edge between 2 vertices represents a dependence or a precedence relationship between those 2 operations. There are 3 types of edges that we can have in a dependence graph that are called respectively a flow dependence edge, an anti-dependence edge, and an output dependence edge. Now, a flow dependence edge corresponds to the situation where the predecessor generates a result that is then consumed by the successor. So in this case, the predecessor writes to R1 and the successor reads from R1. The anti-dependence, on the other hand, corresponds to a situation in which the predecessor uses a value that is going to be overwritten by the successor. So over here, we have the case where the predecessor uses R1 and the successor is going to overwrite it. So it is important that the successor not finish before the predecessor has read its inputs. More often, we will take a conservative view and say that the successor have not even started before the predecessor has started. The output dependence represents the case where both of these operations are writing to the same destination register. And we would like, obviously, that following this, the result in the destination register be the one that was written by this one. So we will require that this not finish until that one has finished. Again, conservatively, we will generally treat this as saying that this should not even have started until that one is finished. Now, the first task of the compiler is to take the code that the original code, which is shown as a sequential list of instructions, each of which must be executed after the previous one unless we prove otherwise, and to come up with a data dependence graph that reflects the essential dependencies in this program. For instance, over here, if we focus on instruction C, it uses as inputs m and n, which are generated by instructions A and B respectively. So there has to be a flow dependence edge from A and B to C. And in this diagram, it is represented by these two flow dependence edges from A and B to C. Similarly, M and N are the inputs to C, but they are overwritten by D and E. So we need to have antidependencies from C to D and E respectively. In this diagram, here are the two antidependencies from C to D and E respectively. And lastly, C writes N, and that is overwritten by D. So there has to be an output dependence from C to D, and we have that over here. In this form, you can analyze every instruction, come up with the appropriate dependencies. In addition to the dependencies, it is common to label each edge with a number, which is called the delay on the edge, and represents the amount of time difference there must be between the start of the predecessor and the start of the successor. If this is a flow edge, this will be the execution time, execution latency of the predecessor. If it's an output dependence, we'll treat it the same way. If it's an anti-dependence, the delay will be 0. Now, having come up with this dependence graph, the scheduler can go ahead and start the scheduling process, making sure to honor these dependencies as well as honor the resource usage constraints that we talked about earlier. At its simplest level, the scheduler for a single basic block consists of the following steps. You start off by initializing a so-called ready list. And a ready list is the list of all the ready operations, where a ready operation is either one which has no predecessors whatsoever, and so it can be scheduled immediately, or one all of whose predecessors have already been scheduled, which can therefore now be scheduled. Now, of all the operations that are ready, we pick the highest priority operation, and there are various schemes for determining priority, and that's not really important right now. Having picked that highest priority operation, we go ahead and schedule it. And here, once again, remember, we want to do it at the earliest possible time, but it has to be such that it honors the input dependence edges to that operation. It can be no sooner than that. And it also cannot be scheduled at such a time that it conflicts with resources that have already been scheduled for preceding operations. So you pick the earliest time consistent with that. Now, at that point, it could well be that we have to update the ready list. This could have been the last predecessor of some other operation. And so now that other operation is ready. We add it to the ready list, and we repeat this process again and again until we scheduled everything. So in the example that we were looking at, we would start off by having A and B in the ready list, because this is just an imaginary node that doesn't really exist. We would schedule A at time 0. That's the earliest time. We could have scheduled B at time 0, except there's a resource conflict, so we'll schedule it at 1. C, therefore, can only be scheduled at time 4, which is 3 cycles after B, and so on. And we end up with a schedule length of 16 cycles. Now, the optimum that we could have managed is determined by the so-called critical path through this computation, which is the longest path from the start node to the end node, which in this case is 14 cycles. The 2 cycles we lost were because of resource conflicts and are requiring to lengthen the schedule to accommodate those. Just to show you what's been going on behind the scenes in terms of resource usage, this is the final resource usage situation for the schedule that we just talked about. And so we have the operations A, B, C, D, and E, and F packaged together as closely as possible, subject to resource usage constraints and the dependence constraints. So this is the final state of the data structure that keeps track of resource usage. Now, one of the problems that we had, which led to the schedule not being as good as it could have been, was the fact that we had lots of spurious dependence edges. These were not all of them essential. They had to do with the fact that we were reusing registers again and again, which led to output dependencies and anti-dependencies. So one approach of exposing all of the parallelism is called register renaming. The idea is that instead of repeatedly assigning to, say, register n, we will imagine that we have an unlimited number of virtual registers, and we will never assign to the same virtual register more than once. So in fact, we will expand the repeated references, repeated definitions of n to being assignments to different registers n1, n2, n3. And similarly, the two assignments to m have become assignments to m1 and m2. As soon as you do this, all of the anti-dependencies disappear, all the output dependencies disappear. You end up with a graph which obviously has far fewer edges, which also is therefore more parallel. The critical path through this is only 11 cycles rather than the 14 cycles that we had before. And that's because E is no longer anti-dependent on D over here. If we schedule this in the same way that we talked about earlier, we end up with a schedule length of 13 rather than 16. The last step is to do register allocation. Now, as a result of having done the scheduling, we know precisely when each result is generated. We know who the consumers are and who the last consumer is of each result. And we come up with what we'll call lifetimes. Each lifetime corresponds to a result that's generated by one of the operations. It starts off at the time that the producing operation is started, and it ends at the time that the last consumer consumes that result. Each lifetime has to reside in some register for that period of time. And so it's clearly not acceptable to try and put two lifetimes that overlap in time into the same register. Otherwise, one of them would overwrite the other before we are through with it. But we can, for instance, pack M3 into the same register as M1 because their lifetimes do not overlap. And this process is the process of register allocation. In this particular case, we can pack M1 and N3 into one register, register R1. N1 and N2 can be packed into register R2, and M2 has to be packed into register R3. So there's a trade-off here. We ended up requiring 3 registers rather than the original 2 registers, M and N, that we had. On the other hand, we ended up with a shorter schedule. Now, scheduling and register allocation is the first example of a type of problem that recurs again and again in compilers. Namely, ideally, we want to do each one before the other one. We saw, for instance, that if we started off with register allocation to M and N, that we ended up having unfortunate anti and output dependencies, which in turn constrained the schedule and led to a poor schedule. On the other hand, if we do register renaming, so we undo all the register allocation, we start off with scheduling first, we get a much better schedule. But then when we get around to trying to pack those lifetimes into registers, we might find that in fact we need more registers than are available. And at that point, we have to introduce spill code. The spill code introduces new dependence edges here, in fact, a totally new graph. And the schedule that we had is no longer good. So we have this kind of a vicious cycle. There are various philosophies as to how one might go about, should one do this first or that first or the two simultaneously. And I won't get into this in any more detail, but I want you to be aware that this is a fairly significant issue. So here's the state of affairs so far. In the example that we looked at, we had 6 operations, and the best schedule that we could come up with was 11 cycles. So that's on the average half an operation a cycle, which is by no means a level of instruction level parallelism to be proud of. And this was caused by the fact that we have data dependencies between operations. The operations themselves have latencies. All of this stretches the schedule out. And typically, you have a branch every 4 or 5 instructions, which means that you don't have a whole lot of operations within a basic block to try and find much parallelism in the first place. So any further attempts at parallelism require that we go to global scheduling, where we try and, in effect, get multiple basic blocks executing in parallel. So having found all the parallelism we can within a single basic block, we want to try and find parallelism between basic blocks. And this is the subject of the next section that we'll get into. Okay, so having found that local scheduling by itself is inadequate, we need to find a way of breaking out of that box and expanding the window that we look at to encompass multiple basic blocks. Now, in this slide, I want to just convey the intuitive idea of what global scheduling is trying to achieve. What we have here is a control flow graph, which consists of basic blocks, and the edges represent the way in which control flow can go from one basic block to another. Let's focus in on this particular basic block, and let's say we've already scheduled it, and this is the kind of sparse schedule we get, not particularly impressive parallelism. What we'd like to do is get the effect of running these basic blocks in parallel, executing them in parallel. So this corresponds to this basic block, and this basic block corresponds to this. And what we have here now is, assuming flow of control went this way, we would have this basic block overlapped with this basic block, which in turn is overlapped with this basic block. And so we'd be getting some amount of parallelism between, in this case, two basic blocks at a time. Now, if this were a multiple thread machine, we could actually do that. We could perhaps have different threads executing different basic blocks. But in a single locus of control machine, we have to achieve that, get that same effect by redefining the basic block boundaries, which are now these bold lines here. And the operations that spill out of these boundaries have been moved either into earlier basic blocks or into later basic blocks. And so finally, we'd end up with this new control flow graph. What we have done in reality is we've moved operations across the basic block boundaries. And when you look at it, you find there's more instruction level parallelism, and each basic block is shorter and fatter. So this is really what we're going to be trying to do. However, there's a problem, which is that we have branches over here. And moving operations across branches is something that can be unsafe if one doesn't go about it very carefully. So let's just review the situation a little bit. Suppose we have a situation where we have an operation in this basic block, and then based on a branch, we go either this way or that way. Now, it is a safe motion to take that operation and copy it into both successors. And the reason this is safe is that regardless of which way we went over here, we wanted to execute this operation exactly once. And over here, we have exactly that same effect. If we go this way, we'll execute it once. If we go this way, we'll execute it once. We have not changed the semantics of the program. So this is a safe code motion. Likewise, if we have a merge in control flow, and I'm afraid these arrows are going the wrong direction, but if we have a merge in control flow, and we have an operation over here, now regardless of whether control flow went this way or that way, we would execute this operation only once. Now, if we take that operation and replicate it in both predecessors, then once again, regardless of which way the flow of control goes, we end up executing that operation only once. And so this is a safe code motion as well. In contrast, here is a code motion that is traditionally unsafe. We have an operation over here that's executed only if flow of control goes this way. If we move it up past the branch, above the branch, then we'll end up executing it even if control flow goes the other way. And since we are now executing an operation that should not have, there's all probability that the program will generate incorrect results unless we take special care. Now, this type of a code motion is called speculative execution, and we'll look at it in some more detail in a couple of slides. There is one other type of unsafe code motion where, again, we have a merge in control flow, and we have an operation that's only on one side. Now, if we move this down here, as we've done over here, we'll end up executing it if control flow goes this way, which is something that would not have happened in the original program. This, again, can be handled by something called predicated execution, which we will get into in a minute. These restrictions on code motion, that is, avoiding unsafe code motions, can be put in a format that a scheduler understands by drawing dependence edges between the branch and operations down here. So in this diagram, the heavy black edges correspond to flow of control, whereas the red edges correspond to control dependencies. And what this says is that this operation cannot be executed until this branch has been executed. And so it holds this operation down below the branch and prevents the speculative code motion that we were that we saw earlier. Likewise, in the case of a merge, we can hypothesize a pseudo operation called a merge pseudo operation, which won't show up in the actual executable code, and draw control edges from these operations to the merge. And again, this will prevent the operation from moving down below the merge. Let's philosophize for just a minute as to what we are trying to achieve with a branch. Really, what we're trying to do is make sure that this operation is executed only under certain conditions. More precisely, if flow of control came to this particular basic block, and if the branch was such that it went in this direction, only then do we want this operation to be executed. And there's a compare over here that determines whether the branch went this way or not. So what we're saying is, if flow of control comes here, and if the compare is such as to force the branch in this direction, then and only then do we want to execute this operation. Otherwise, we want to avoid this operation by going around in a different way. Now, there's a different way of achieving the same effect, and I'd like to talk about that. But first, I need to spend a minute to talk about some hardware support that we need to postulate to make this possible. To begin with, I want to talk about the predicated operation. This is a fairly conventional operation. It has two data inputs. It might be pipeline, and at the end of it, it writes a result and perhaps generates an exception if there's some error. Now, what we'll add to this is a third input, which is a Boolean input, a predicate input. And the way this operation will behave is that if this predicate input is true, then this operation will execute as normally. If this is false, the operation will be squashed. So no result will be written, no exception will be flagged. We will also postulate a slightly different form of compare, which has a third input once again. Normally, what we would have in a compare is two data inputs. We'd compare it, and we generate a Boolean result, a true or a false. Now what we will do is we'll add a third input, a Boolean input, and we will take the result of the compare, AND it with this, and that is what we will write out. The way we intend to use it is that this predicate input corresponds to the condition under which this compare would have been executed. And this compare corresponds to the condition under which the branch would have been taken. And therefore, this result over here corresponds to the situation in which we would have arrived at a particular basic block, and we'd have taken the branch. Now, with those two operations in our back pocket, let's re-examine this issue of controlling when and whether this operation executes. Now, once again, this operation is supposed to execute only if flow of control came to this basic block, and if the compare was such that the branch would have gone this way. Now, if you replace the normal compare with this new compare that we just looked at, which has a predicate that corresponds to control coming to this basic block, which generates a result, which is the AND of control coming here and the branch condition being true. And if we take the output of that compare and provide that as the predicate input to this operation over here, now we can take this operation that used to be over here and move it down here, and we don't change the semantics. The reason is that if in fact flow of control would have come this way, then this predicate will be true and this operation will execute, which is exactly what would have happened here. If in fact flow of control went the other way, then the result of the compare would have been false. The output of this compare would be false, and this operation will not execute, which is exactly what we want over here. So with this predicated execution capability, we can now move an operation down past the merge, which previously, remember, was an unsafe operation, and we still retain safety. We retain the original semantics. Now, interestingly enough, not only can we move it down past a merge, but we can also actually move it up past a branch. So in this case, what we've done is we've taken this operation, moved it up past the branch, but it's still below the compare operation. So it is still controlled by this predicate, which is true if and only if flow of control would have gone this way. So this operation will execute if and only if flow of control would have gone this way. So there's an interesting new situation here. We've now moved an operation up past a branch, but it is not predicated, it is not speculative execution, because we already know the predicate under which this operation should have been executed. So there's a little bit of new thing that we have to get used to over here. Now we could do something much more radical. We could take every operation over here in these three blocks, one by one move all of them up into this basic block, all of them under the appropriate predicate. And at this point, these branches become pretty useless because they're just steering us through empty basic blocks. We could eliminate the whole thing, and we are left with just one basic block, which makes use of this predicated execution. So there's no more control flow. And this style of code we will call if conversion. So we take what used to be a control flow graph, replace it by a single basic block which has no flow of control, but which has all these predicated operations in it. Finally, we might move this operation not only past the branch but beyond the compare. And at that point, it stops being predicated execution, and it is now a speculative execution. Because we do not at this point know whether this operation should be executed or not. We do not have the predicate that is needed to control it. So it will get executed regardless of whether flow of control goes one way or the other. And that is the definition of a speculative instruction. So we have a new definition of speculative execution compared to the previous one. Previously, we said an operation was speculative if it was moved up beyond the controlling branch. And now the way we look at it is that an operation is speculative only if it is moved up beyond the compare that determines its predicate. Now there are some potential problems with speculative execution or speculative code motion. One is that since we'll be executing this operation under conditions in situations where it should not have been executed, there's the danger that it will override either a register result or a memory location, which it should not have overwritten, because in fact it should not have been executed at all. There are a couple of ways of handling the register case. One is to have shadow register files which hold the speculative result until we are sure that those operations should have been executed, at which point they're committed to the official architectural register file. The other approach is to use renaming, which we've seen before. And what this boils down to is we just have to have more architectural registers than we would have had otherwise, so that we can accommodate the renaming. We don't have the memory problem at all unless we have speculative store operations, because those are the ones that change the contents of memory locations. If we do have speculative store operations, then we have to go to some equivalent of the shadow register file, except of course it's a sparse copy of memory. It's an associative buffer that into which we deposit the speculative store result, but it's not actually committed to memory until we are certain that it should be done. There are two or three other problems as well. One is that we do not want to generate a spurious exception. In other words, the speculative operation might generate an exception, but it turns out that that speculative operation should not have been executed at all. And nevertheless, if we go ahead and flag that exception, we end up with getting exceptions that weren't there in the original program and would not have occurred if our compiler had not done this speculative code motion. There are other problems that go beyond that, namely trying to precisely locate which operation caused an exception, that is, assuming this is a non-spurious exception, and finally trying to recover from these. I won't get into these at all. These are very complex topics which aren't very well understood today. But let me say a couple of words about preventing the generation of spurious exception. Now, one approach is to only speculate those operations that just can't generate exceptions at all. And so there's no issue of spurious exceptions. And the types of operations that fall into this category are, say, logical shift operations that can't generate an exception, integer operations such as integer adds and subtracts, if there's no overflow exception defined on them, or loads and stores from statically declared scalar variables, which are guaranteed to not be out of the virtual space, address space of the program. That's one approach. The other approach, a rather radical approach, is to say let's just turn off all exceptions. Let's throw the baby out of the bathwater, we'll avoid the problem of generating spurious exceptions by also eliminating the ability to report true exceptions. And that one, could leave one feeling quite uncomfortable as well. And then there are schemes which have been suggested, 2 or 3, which suppress all the spurious exceptions, but do go ahead and report the true exceptions. And I'll refer you to the bibliography at the end of the talk as to how that might be done. Now, a common misconception is that an operation is dependent, control dependent, on all of the branches that precede it, or in our kind of new think, that an operation is control dependent on all of the compare operations that precede it. And in fact, that's not the case. Let's look at this example over here of a control flow graph, and these represent the basic blocks. If you consider an operation that is in this basic block, and you ask the question, when am I sure that this operation is going to be executed? The answer is that it does not depend on which way this branch goes. It does not depend on which way this branch goes. In fact, once flow of control arrives at A, regardless of which way these branches go, we know we are forced to execute basic block E. So in fact, all the operations in E are control dependent on precisely the same compare that decides whether A should be executed. Now that is represented over here in a what's called a control dependence graph by showing the same control dependence going to A, to E, and for that matter H. Because with H as well, as soon as we know that we're going to execute A, we know that there's no option but to execute E and no option but to execute H. So all of these are under the same control dependence. A more interesting case would be, say, basic block D. If you consider an operation over here and ask the question, when is the earliest we know that this is going to be executed? Well, if we are in basic block A and we branch this way, then we know we'll definitely execute D. So we have a control dependence edge from the compare over here to all of the operations in D. The other situation in which we are sure that this is going to be executed is if we have come all the way to basic block B and then we branch this way. So over here, we'll have a control dependence edge from the compare over here, the correct sense of the compare, to the operations over here. So what the control dependence graph does is much the same as what the data dependence graph did for data dependencies. The data dependence graph eliminated all the spurious data dependencies in the sequential code and came up with only the essential ones. And what the control dependence graph does is it eliminates all the apparent control dependencies that you might expect from the control flow graph and shows you only the essential ones. Now what this control dependence graph does is it also, as a result, exposes further parallelism. Since the instant we know that A is going to be executed, we know that E is going to be executed and H is going to be executed. We could, in fact, start executing all of them in parallel, assuming that there were no data dependencies between the operations in A and E and H. So in fact, we could have the following type of situation. Here's the control dependence graph that we looked at before. And here's one possible parallel execution of that computation, exploiting the control independence that we've just recognized. And this permits this computation, this computation, this computation, all of them to execute in parallel. Now, within each of these computations, there'll have to be some amount of sequentiality that is determined by both these control dependencies and any other data dependencies that exist. Now, the question one might ask is, how do we actually exploit this? I mean, in principle, we can do this. And in fact, if we had a multi-thread machine, we could go ahead, assign this to one thread, assign this to another, this to a third, and make use of this parallelism. If we have a single thread machine, we have one of two choices. One is to come up with a rather complicated piece of code which says, okay, I start off executing these three in parallel. At some point, this thing branches either one way or the other. So I'll have two versions of code, one corresponding to it having branched this way and executing in parallel with this, and the other corresponding to it have branched the other way and executing in parallel with this. Then we run into the next branch. We'll split those two pieces of code into 4 pieces of code, and so on. And so with a fairly large explosion in code size, we could end up with a single locus of control program which exploits all of this parallelism. The other approach is to do if conversion. Recall, if conversion was one where you get rid of all of the control flow by using predicated execution. And in that case, you can think of these control dependence edges as being essentially the predicates. And so the predicate for D is determined by this compare and that compare. Once we can get rid of all the control flow and have this predicated execution, then it's a single basic block. We can schedule it just the way we did a single basic block earlier and still exploit this parallelism. Now, there are other situations in which, in fact, there isn't control dependence, but the control dependence is disambiguated early enough that we still get a lot of parallelism. Consider this loop over here with this particular control flow graph. And there's a compare down here that determines whether we are going to execute the next iteration of the loop or not. Assume further that the data dependencies on this compare operation are such that we could actually have moved the compare all the way to basic block A. So now if you look at the control dependence graph, we get something that looks like this. Ignore for the time being this part of the arc. So we have a control dependence from the previous iteration that determines whether this iteration is to be executed. And within this iteration, we have these further control dependencies. And what this arc says is that a compare in one iteration determines the control dependencies for the next iteration. The one over here says that this control dependence spans one iteration. If we look at the parallel execution of this loop, we get something like this, where each color represents one iteration of the loop, the first, the second, and the third. Here's the compare in the first iteration that determines whether the second iteration is going to be executed. Here's the compare in the second iteration that determines whether the third iteration will be executed, and so forth. And once again, you see that there's a large amount of parallelism across the multiple iterations of the loop, and that we are not doing any speculative execution. So this is a very important thing to bear in mind, that you do not have to assume that when you move operations past branches that you are necessarily resorting to speculative execution. And very often, particularly in things like do loops, there's large amounts of parallelism even without speculation. So over the last few slides, we've seen ways in which we can relax the constraints on unsafe code motion so as to move operations to earlier and following basic blocks. And that is the leeway that we need to be able to do global scheduling, which, as you recall, is fundamentally a task of moving the appropriate operations from one basic block to the other so that they can be scheduled with other operations with which they can be executed in parallel. Now, if you recall, when we talked about scheduling a single basic block, we had a reasonably simple process of picking the highest priority operation, scheduling it, updating the ready list, and then repeating the process. In the case of global scheduling, you might imagine that the process is the same. It turns out to be considerably more difficult. To begin with, we might start off by picking the highest priority operation. But actually here itself, things get a lot more complicated. Whereas in the case of local scheduling, there was only one block, there was only one execution path that we had to consider. In the case of global scheduling, there might be multiple basic blocks that and multiple flows of control through that code. And the priority of an operation can differ depending on which particular execution path we are considering. So even the issue of priority becomes a lot murkier than it used to be. Let's say we pick an operation somehow. The next thing is we want to schedule it. Now, scheduling is essentially a code motion problem because we are reordering the computation relative to what it used to be. It might have been following some other operation initially. After scheduling, it might precede it. Now, if in fact scheduling ends up in interchanging its order relative to a branch, then we are doing interblock code motion, and we now might need to replicate the operation, unify it, etc. So along with the act of scheduling it, we have to restructure the data dependence graph with additional operations. Then we have to update the data dependence graph. Again, more complexity. Along one path, an operation might be ready. Along another path, it may not be ready. So how do you define readiness? And finally, we have to update these scheduling priorities. And as I explained, the priorities are fairly complicated and path dependent. So what used to be a rather simple process does not immediately extrapolate to an equivalently simple process when we start scheduling across basic blocks. So there have been a number of different philosophies that have developed as to how one copes with a problem. One approach, all of these approaches are somehow trying to simplify this problem by decomposing it into simpler tasks. So one philosophy is first do all your interblock code motion. Somehow get it right, move the right operations into the right basic blocks. And then once you've done that, just go ahead and schedule each basic block individually, as in local scheduling. So the idea is that the code motion put together in the same basic block those operations that were independent of one another. And therefore, the local scheduler would end up being more successful. The other approach is, might seem strange at first. It is first just schedule it, ignore all code motion, and then come back, look at the schedule, and figure out, in fact, what kind of code motion was implied by the schedule. Almost all of these approaches, one way or the other, find a way of looking at the multiple basic blocks that have to be scheduled and making them look like a single basic block. And so you make it look like a single basic block, you schedule it like a single basic block. Then you come back and you say, well, it wasn't really a single basic block. There was some code motion implied. What is it? Let me do it. And then there's a third approach, which is to try and do this code motion and scheduling simultaneously, which has much of the complexities that I mentioned in the previous slide. Now, at a philosophical level, at a theoretical level, you can argue all you want about which one is better, and there is no way of settling the argument. Really, the issue gets down to one of engineering. This is an engineering problem. It's a matter of how do you get most of the performance that you could get in the ideal case without paying the very heavy price. And for instance, over here, you could argue that the code motions that you did were not the best ones, and therefore you'll get poor performance. Over here, you compromise performance by picking a scheme that allows you to make it appear like it's a single basic block. And we look at 2 or 3 schemes. And then you do the scheduling. So you compromise the performance up front, perhaps. Here, the major concern is that even though you might, at least in theory, not compromise performance, that your the complexity might be extraordinarily high. It turns out that all the global schedulers that have been productized to date fall into this category. And let me talk to you about a couple of those approaches. One approach is what is known as trace scheduling. And it depends on the concept of a trace. A trace is a linear sequence of basic blocks, contiguous basic blocks, which are acyclic. So here are 3 basic blocks, A, C, and E. They each follow one another. They're contiguous. They're linear. There's no branching involved. And they're acyclic. Now, the basic idea of a trace scheduler is to say, let me pretend that these 3 basic blocks are all just one basic block. I won't treat the branches that I have in it or the merges that I might have in it as any different than an add or a multiply. I'll go ahead and schedule it. And then once I've scheduled it as if it were a single basic block, I'll look at how the operations have been reordered relative to the branches and the merges. And that will tell me which operations in effect were moved across basic blocks and needed to be replicated. So let's say we went through that process. We pretend that this is a basic block. We come up with this schedule. And let's say that in this schedule, this is where the branch from A has been scheduled. This is where the merge at the top of C was scheduled. And remember, merge is a hypothetical pseudo operation. And here's where the branch at the bottom of basic block C was scheduled. Now, if we examine the schedule and we find any operation that used to be in basic block A, and if we find that it is below BR1, then that corresponds to an operation that was moved from A down below the branch and has to be replicated on both this path and on this path. Now, on this path, it already exists. We have to make sure that that operation gets replicated over here. And that's what all these A prime operations are. In a like fashion, we can determine which operations from, say, E moved up past the merge and should be replicated in B. And those are these operations over here. We can look at which operations from C move down past BR2, which are over here, for instance, and have to be replicated over here. So by maintaining the pretense that these three basic blocks were actually a single basic block, we greatly simplified the scheduling task. We could fall back on the very simple scheduling algorithm we had for a single basic block. And then we examine what comes out of it, and we figure out what code motions were implied by that particular schedule, and we perform them. So this is an example of schedule first and then do the appropriate code motion. Now, there are some issues having to do with how we actually select and build these traces. Trace scheduling is a scheduling philosophy that subscribes to doing the most frequent part of the program first. So we'd start off by defining a trace based on execution frequencies. We would start off by focusing, for instance, on the most frequent basic block, then growing a trace out from it, above it, below it, by following the high frequency transitions between basic blocks. And then we'd cut it off at some point when the frequency of execution gets too low, and that would be one trace. After we've scheduled that trace, we would then look at the remaining code. We'd pick another trace and just keep repeating this process. Now, the execution frequencies themselves could either be gathered by profiling the code, instrumenting it, and figuring out, in fact, which basic blocks are executed how frequently. Or one can use heuristics that provide you with a large part of the value of detailed profiling. The trace growing heuristics themselves can be quite complicated. In addition to the execution frequencies, a number of other issues are often taken into account. For instance, if you have a procedure call in a basic block, that could break a trace, and a number of other such considerations. And as I mentioned, these traces are not only picked but scheduled in decreasing order of execution frequency. And what that tends to do is it tends to take the most frequent part of the code and schedule that in preference to the rest of the code. And then you take the less frequent part, and it has to adjust to the schedule that was put in place for the most frequent trace. But it can ignore the needs of the rest of the code, and once again optimize the trace, ignoring the rest of the program. So you end up with getting very good schedules for the most frequent parts of the code, and not so good schedules for the less frequently executed parts of the code, which is precisely what you'd like to do. Now, one criticism that has been advanced about trace scheduling is that it can only cope with a linear trace. Now, suppose in fact we had a region of the code where all of these basic blocks were approximately the same frequency of execution. So that it would have been very difficult to pick any one linear sequence of basic blocks as the trace. So what we can do is we can start out by defining this using various heuristics. And then we can go through a process of if conversion. Now recall that if conversion was a situation in which we moved all these operations up non-speculatively into the first basic block. And we moved it up non-speculatively by making sure that every operation remains dependent on, and it will be scheduled after the compare that determines the predicate. So as a result of moving all these things up, you end up with one single basic block, which contains the computation that originally used to be in these 5 basic blocks. So the kind of vague outlines of the basic blocks A, C, F, D, E is supposed to indicate that these basic blocks have kind of dissolved and the operations have spread out all through this one new basic block. Once again, remember these basic blocks were empty. We can discard all of them and we're left with just this. We could have, if we had wished to, retain the merge that existed from the basic block B into here. Or we can just replicate all of the control flow graph that follows the merge and have one copy that's dedicated to this region and one copy that's dedicated to B. And in fact, that's what we've done over here. So in this particular case, we chose to eliminate the merge over here. Having done this, we can ignore this. This is the part that we are trying to schedule. This now looks like a single basic block. We can go ahead and use the same scheduling algorithm we used for local scheduling. And if in fact we have predicated execution hardware, then we are done. And this is once again a case of where by making it appear that this was a single basic block, we ended up with a much simpler scheduling algorithm. If in fact we don't have predicated execution hardware, then there's a technique called reverse if conversion, which essentially goes in the reverse direction, regenerates the control flow graph. And however, in this new regenerated control flow graph, we will end up with all the code motions that were necessary to achieve the schedule. Now, in the previous 2 cases, we are considering acyclic code. And now I'll consider one example of a loop. So what we have over here is either a single basic block, it could be an if converted region, which now looks like a single basic block, or it could be a trace. For our purposes, from the scheduler's point of view, it is as if it were a single basic block. Previously, we were trying to get parallelism by executing multiple basic blocks in parallel, whereas over here, we're going to get parallelism by trying to execute multiple iterations in parallel. We will also insist that every iteration have an identical schedule, and that these things, each iteration be started at a fixed interval relative to the previous one. Now, just as in the acyclic case, we achieve global scheduling by moving code from one basic block to another. Here we achieve global scheduling by moving code around the back edge, essentially from one iteration to the next. But instead of trying to first decide how to move it and then do the scheduling, we will once again try and schedule first and then decide how it should be moved. So in fact, what we will do is we'll come up with a single schedule for one iteration, but we will design it in such a way that it interleaves with the resource usage and the data dependencies of all the different iterations. In particular, if we have an operation here that is scheduled at a particular time, then it means that exactly one initiation interval later, the same operation from the next iteration will be scheduled. So we can not schedule anything else in this iteration that conflicts with that. Likewise, one initiation interval later, we have another operation, the corresponding operation from the third iteration. We cannot schedule anything here that conflicts with that. So we end up with a constraint that says you can never schedule 2 operations that use the same resource at the same time modulo the initiation interval, or II. And this is modulo scheduling. The issue is, how do we decide that initiation interval over here? And it is determined by taking the maximum constraint, the worst case constraint between 2 factors. One is that we cannot initiate successive iterations at a higher rate than the critical resource, the most heavily used resource, can accommodate. So if, for instance, we have 6 add operations per iteration and 2 adders, we cannot initiate this sooner than once every 3 iterations. Also, if you consider an operation over here that is the predecessor directly or indirectly of a second operation, which in turn is a predecessor of the first operation but in the third iteration, then we know that there are 2 initiation intervals that separate these two, and that must be at least as large as the path length from here to here. So these 2 types of constraints, which are called respectively the resource constrained minimum initiation interval and the recurrence constrained minimum initiation interval, together determine the minimum initiation interval, which is the max of these 2. And once we have that, we go ahead and schedule this as if it's a single basic block. And once we've scheduled it, we know that, in fact, these are the operations that are scheduled in the loop. These are the things that had to be moved out into a prologue and to an epilogue. Another example of schedule first and then do the code motion. There are other scheduling schemes as well, which I won't have the time to go into, which look at which are variants of either trace scheduling or generalizations of trace scheduling, or of the if converted scheduling that I mentioned. And likewise, there are other schemes for handling loops, which again I'll refer you to the bibliography to try and understand further. Now, so far we have acted as if scheduling for a superscalar machine is identical to the task of scheduling for a VLIW machine. In fact, there are some differences. We don't fully understand yet what these differences are exactly, but let me point out 2. One of these is, you might call, an opportunity. Recall the resource usage patterns that we had before, the reservation tables. For the floating point add, it said that we use the input buses here, we use the adder here, and then we use the result bus over here. Now imagine we have a dynamic arbitration on the result bus. What could well happen is that if on the cycle that the floating point add operation wanted to use the result bus, if it turned out that the bus was busy, one might delay the usage of the result bus by 1 cycle, and the add would just sit in the floating point adder an additional cycle. So effectively, we'd get a reservation table that looks like this, where in fact the result bus usage is delayed by 1, and we use the floating point add for 2 cycles. If due to arbitration you delayed 1 cycle further, then you get this pattern, where again what's happening is this region is just getting stretched by as much as the delay in getting to use the result bus. Now in a VLIW scheduler, this is the only pattern available, and the scheduler would have to use this pattern or schedule it at a different time. Whereas in a superscalar machine, the scheduler could say that, in fact, I have a whole family of patterns available, and I should use the one that gives me the best schedule. So here is an opportunity which it's not quite clear how we'd use, but it results from the fact that the hardware does have some dynamic capability, and the compiler should try and make use of it. The other problem you can think of as a negative, which comes about from the fact that in most superscalar machines, there's the desire to have precise exceptions. And let me explain how this works. Suppose you had this simple data dependence graph in which B and D have very long latencies, 7-cycle latencies, and the rest of the operations have just 2-cycle latencies. Here are 2 legitimate schedules for the same graph. In one, we schedule A, B, C, D, E, and F in this order. And since F is dependent on B and D, it can't start until these have finished, whereas these are all independent of one another and can start one every cycle. So I'm also assuming here that this machine is capable of only initiating 1 operation a cycle. Now, what a precise exception requires is that if B had an exception, I should be able to get the machine into a state in which A and B have executed, but C, D, and E have not. But given the fact that the latency of C is really short, what I'd find is that by the time B finishes, not only C but E have completed, and I won't have a precise exception. Now, the way this is handled in superscalar machines is that there's something called a reorder buffer that holds the result of C and only commits it to the official register file after the result of B has been committed. So you have this kind of a situation where these shaded squares correspond to the act of retiring the result in committing it to the official register file. And there's this constraint that these happen in precisely the same order that the operations were initiated. If we had only two reorder buffers, what we would find is that we can start A off and B off and C off on schedule. But we'd like to start D over here, but there are only two reorder buffers. They're in use by B and C. And so we have to wait until B finishes, release the reorder buffer, and then we start D. And the net result is that the schedule, which used to be, I believe, about 15 cycles or thereabouts, has been stretched out to 18 cycles because of this. Now, if we had been fortunate enough to have chosen the second schedule, then even though we have exactly the same constraints, that the operations finish in the same order, that they be retired in the same order, it would turn out that there'd be no impact on the schedule, because by the time each operation requires a reorder buffer, it has already been relinquished by the previous one. So clearly there's because of this reorder buffer issue, there is a fair sensitivity to which schedule one chooses. However, there's no good understanding as of yet as to what heuristics one uses to get the right schedule. Perhaps viewing the reorder buffers as yet another register file that needs to be accommodated is one way of going about it. But again, as I said, not much is known about it. This is one of two companion talks. And in the next talk, I'll be talking about exposing ILP and enhancing ILP. In this talk, we looked at how you exploit it once you've done this. I'll say a little bit about engineering ILP compilers and how that differs from conventional compilers, and a little bit of perspective. In the rest of the tape, at the end of the tape, you will find a few references that will get you started on literature in this field, plus a pointer to a more extensive bibliography.